Hi everyone, and today I'm very privileged to invite Daniel to talk more about his work on large language models and robotics. So the history was that I wanted to do some work on agents and cooperative agents in a grid world, like in an escape room. So I set up a hackathon team. All right, and Daniel said that, oh, he did some work similar to that before. So I got very interested. Like, how is he going to use agents on like his environment, like the mini grid environment and so on? So today, Daniel will be sharing more about his work, and I'm very excited to see what he's doing. So Daniel is currently a PhD student at UCL. So I'll leave him to introduce himself. Daniel, please.
Yeah, hi everyone. I'm currently a PhD student at UCL and going into my second year. I am interested in how to get to generalist robots, so robots that can do a wide variety of things in lots of different environments in the world. And LLMs are really like a powerful new tool that we have for making progress towards this. So today I'm going to share a bit on my general thoughts concerning robotics and a survey of like different ways that I've seen LLMs being used in the field. And we'll conclude with like a simple end-to-end example covering my previous work on using LLMs in MiniGrid and then like some ideas I have for future work. So yeah, really happy to be here today, and thanks so much to John for organizing this.
All right. So without further ado, let's go with the presentation. There's a total of 80 slides here, so so let's hope we can end it in time. But yep,
Yeah.
let's go for it. Yep.
Okay, yeah, so I've decided to title the talk Scalable Robot Learning in the Age of GPT. And this reflects like how we can try to think about using LLMs for robot learning. And next slide, please. And what is the motivation? So as I said, we want generalist robots. They're kind of like a holy grail of robotics that we've always wanted to have. And the idea is we need really multitask capabilities. So imagine a robot that can do like any household chore that you ask it to do. There's some examples listed here. And to do this, the robot has to be able to understand, a wide variety of objects and execute lots of different kinds of manipulation skill. And we also want such a robot to be able to function in diverse environments. So not just your house, but anyone's house, or maybe not even a house, like outside in the world, for example. And this is like staggeringly difficult. We've not achieved that yet, and we're probably not very close to achieving that. But how might we achieve that? Next slide.
Yeah. By the way, this is my life goal as well. Uh, Fast and
Nice.
adaptable agents.
Yeah.
All right.
Yeah, so I'm going to propose an oversimplified definition of intelligence, of mapping from thoughts to actions. And on the left, we have thoughts, which are highly abstract, and on the right, you have actions, which are highly concrete. They're concrete things you do in the world to change the world state, and you get feedback from that. And often we have, this middle layer of intentions, which represent like the immediate, high level thing you want to do next. And I'm going to argue that LLMs are trying to solve this sub-problem of mapping the thoughts to intentions. Okay, you can agree or disagree, but we can discuss it later. And robotics is solving the problem of mapping intentions to actions. And so it's natural to think about, next click. Oh, sorry, never mind. It's natural to think about how we can connect both of those together. Yeah, and I'll just talk a bit on the robotics side of things first, like introduce the formalisms, and then we'll see like how it connects back to LLMs. So yeah, next slide. Okay, so in robot learning, we a very general and like useful way to think about it is just deriving low-level robot actions from robot observations. So the observations people have converged largely on like egocentric camera views as the observation because it's really general and it can be used across like different robots, different tasks, different environments, etc. Everything can be described with images essentially. And low-level robot actions are something that's more robot specific, but you can think of those as typically like the position of the gripper or whether the gripper is open or closed, something like that. And we want an end-to-end mapping, it's called a robot policy, that takes in the current observation and tells you what action you should do. And in the multitask case, next slide, we can also see that there's usually a goal. Yeah. Okay, so I'm going to summarize all the progress in robotics as follows. Go back one slide, please. Yeah, as multitask imitation learning is surprisingly effective. It's so simple. You just have a data set of demonstrations of different things you want the robot to be doing. You see there's like language annotations here. And you just do supervised learning on that. You just train the robot to mimic the expert demonstration for all the demonstrations you have, for all the tasks you have, for all the environments you have, and it works. Really simple, really clean. This is like the most ideal setup you could possibly have. Next slide. And some of
Just
the
one question on this. The
yeah,
imitation must be also from egocentric view, right? Must be the view of the robot. Can you learn?
yes, right, yeah. So that is definitely the simplest case. There is work that explores like using different like views, but yeah, generally, you want to have as small domain shift as possible. So it's best to learn from the same view,
Understand?
egocentric and egocentric.
The reason why I ask is like I think humans learn by imitation as well. But you probably like as a kid you imitate your parents. That is not an egocentric view. You see someone do an action like
Yeah,
walk. You try.
right.
I'm just thinking like how to incorporate that into a robot.
Okay,
Yeah.
yes.
I mean, if you're
We're,
talking about
we're
that later, we can do that later as well. Yeah.
we may get to this. That is also like something I'm highly interested in. Is kind of the other half of my PhD. This is one half, and like learning from videos is the other half. But yeah, let's talk about that more at the end. Okay, so next slide. Yeah, and some of the capabilities of this multitask imitation learning setup are ability to execute new tasks without having seen them before. So after you've like pre-trained on this variety of diverse tasks, you find that the robot is able to just, a priori map a language description to the action sequence that it should take in order to execute that description of the skill. Here you can see like there's an example of placing the grapes in the bowl on the left and pushing the bowl across the table in the middle and wiping the tray with a sponge on the right. That one's kind of, it's not really doing a wiping motion, but it's got the idea. So yeah, like the promise of massive pre-training is like generalization in a robust way to new things. Next slide, please. And the general recipe of data plus imitation learning has given us these really powerful instruction following model, such as RT1, Robotics Transformer 1. This is the work being described here, which exhibits generalization to diverse tasks. It's robust to the background. You can put in any environment, it'll kind of work. And it can do like fairly long horizon things. If you look at the instruction on the top left there, it's pick an apple from the top drawer and place it on the counter. So this actually involves like a bunch of sub steps, like first opening the drawer and then taking out the apple and then putting it on the counter and then closing the drawer again. And somehow the robot's able to internally reason about all these things that it has to do and do them in the correct sequence. Next slide, please. So scaling this paradigm is what I believe gets us to a robotics foundation model, which would be able to do those general household tasks that we talked about at the start. In this slide, we're looking at Gato, which is like a generalist agent trained on a diversity of interactive domains. Some of them are Atari games, some of them are like simulated quadruped dogs, like robot arms. And you can see that pooling lots of diverse kinds of data together creates a model that's capable of doing all the things. Actually, you can still even like ask it questions and it will answer correctly, as you can see there. And like it understands, it can answer questions about images too. So possibly like we already have a pretty good recipe for getting to generalist robots. Next slide, please. Okay, so what's the catch here? The catch is that data is kind of the bottleneck for doing stuff like this. When you have like Yeah, so we can scale models pretty well, but data is like much harder to scale because traditionally such robot data sets need to be collected manually, as in you have to have a human who teleoperates the robot to collect demonstrations of things that you want the robot to do. And this is kind of the dirty secret of lots of robot learning works. It's not the method, it's kind of the data set they use.
So this is
Yeah,
like the data is everything paradigm.
pretty much, yeah.
Yeah, I mean,
So,
if
so
you look at Gato in the previous one, they actually learn from expert demonstrations for all of them. They
mhm,
don't start from scratch.
right,
So
exactly.
yeah, so the key question in robotics that I have for people doing it is that, like, yes, you can have data of experts, but how are you going to get the experts in the first place?
Yes, yeah. So yeah, normally it's the simplest way is you have a human, you could have like a single task expert that you train. Of course, that introduces like additional complexity into your pipeline. So yeah, so you're exactly right. How do you get the expert data in the first place is pretty much like the central question that we need to answer. And you can see there's on the left, there's the chicken and egg problem where you need the policy to get data, but you need the data to get the policy. So you kind of have to bootstrap yourself into starting somewhere in order to like really like allow for self-improvement. Okay, so next slide, please. Okay, and lastly, like what kind of data do we need? So I'm going to argue the data we need is semantically rich data. It's data that changes the environment state in interesting and meaningful ways. So on the left here, we have a demonstration of a gripper picking up. Okay, actually, what if I told you the task here is pick up the spoon? Okay, so obviously it's not doing that, but this is still kind of changing the environment in an interesting way because it's picking up the pot and it's moving the pot to a different location. So that could be like something else that the robot finds useful. Whereas on the right, the task is to just like pick up something and the gripper is just going around randomly and it's not really doing anything. So it's kind of not useful for learning a good policy because it didn't achieve anything meaningful. And this is and so we need the data, the kind of data on the left is what we need. And the data on the right has proven not to be very useful for robot learning. But the data on the left is really difficult to collect because like how do you imbue robots with this like semantic awareness, right? You have to have humans. That's why you need to have humans to collect such data. Next slide, please.
Yeah, for now, you need humans, but
Yeah,
I
for
think
now traditionally you need humans, yes.
yeah, I mean, I do have methods that I'm working on now that can potentially help with learning from any kind of transition in the environment. It's called learning fast and slow. But happy to
Okay.
discuss more once we reach the end. Yeah.
Yeah, cool. Right. So yeah, we can think about this again as now that we understand the robotics context, we can kind of see the pros and cons of the two lines of work here. One is robotics, on the one hand, it gives you grounded feedback about the environment, but as we've discussed, the data is used for robot learning is really hard to scale up. And I don't think that if you just kept collecting data in the way that we do now, it's not going to scale to like all the things that we want it to do. And on the left, we have actually LLMs, which have benefited from text pre-training. So that is way more scalable than robot data because you just need internet text. Like as when people type something in a forum online, it can be added to the collective database of human knowledge that trains an LLM. But it's not grounded. So it's text. It is not feedback in the real world. You don't get consequences of your actions. And arguably that's a cause of like lots of failure modes of LLMs. So how do we, merge these two components together? How do we connect LLMs to robots for decision making? And how do we like particularly see this as a way to scale up the bottom-up robot learning, if that's possible? Because that is what you want eventually, I think, if it was scalable. Okay. Next slide. Yeah, so the remainder of the talk is going to be about, firstly, I'm going to cover how can LLMs accelerate robot learning. Then I'm going to talk about some preliminary work that I did on this in MiniGrid. And lastly, I'll cover some interesting future directions. Next slide. Okay, so before we dive into things, a note on perception modes. So we previously said that the robot observation is low-level sensor data. So this is mostly a camera image, but you can also think of other things such as like tactile information, proprioceptive information like your internal accelerometer, etc. And the LLM input is a text. So how do we, reconcile these different modalities? Next slide, please. And I don't think this will actually be that big of a problem. So for just making progress quickly on like a problem that you care about, you can write a manual, text description pipeline. Of course, it involves some effort, but like if all you care about is that environment, then it's probably worth to invest this effort just to like see whether an LLM can benefit from that. And an example here is the NetHack language wrapper. So NetHack is kind of a game-like environment where people got involved. It's actually a really complex game-like environment that's not been solved by like previous, learning-based approaches. And so this language wrapper is something that enables LLMs to contribute towards solving that environment. In the middle, we kind of have this new development of visual programming. I actually found this really interesting, where instead of like understanding the scene directly, the LLM can write code to parse the scene. So as you can see here, there's an image, and you can ask the LLM a question, and the LLM, instead of like answering the question directly, it outputs a program that you can run to answer the question. And when you run the program that predicts no. So are there both ties and glasses in the picture? The program searches for ties, it searches for glasses, then it does a Boolean it does a Boolean and the answer for this particular image is no. And actually the nice thing about this program is not just good for this image. You can toss the image and replace it with any other image. It will still answer the question for that image. So that's like a pretty scalable way to, do perception. And lastly, we can come to multimodal LLMs like GPT-4. Some of you may have already gotten the chance to play around with the Chat GPT-4 that has image enabled. And next slide. And if you do that, you may like see it has really good visual reasoning capabilities. So this is from the GPT-4 technical report. So there's an image on the left. This is like actually a Reddit meme, and the question is, what's funny about the image? And GPT-4 is able to look at this and understand what's funny about it. So if it can do some kind of complex visual reasoning task like this, which this is pretty high on the level of like semantic understanding. So we can argue that future LLMs will not need like a custom perception pipeline to understand, sensor data. So assuming this problem will be solved eventually, we can just use like a hacky method for now, and eventually, with the understanding, that will be replaced by something better. So it's okay to use like manual text description pipelines, in my opinion, as long as your motivation is, well, this is not the problem that we actually care about. It's just like something we have to do. So like any method to solve it is okay. And then in the future, this will be solved naturally, if that makes sense. Next slide, please. And yeah, and another perspective is we don't actually need LLMs to be perfect. Of course, if you're using LLMs as like the final system to control an agent, that puts like a very high standard of performance on the LLM. But we don't actually need that, because we can see LLMs as just a stream of diverse and semantically rich data. So this is a work where they used LLMs to orchestrate, different code modules to collect diverse kinds of data, exploring in a semantically aware way. And then that data was just used, it was filtered, and it was used to train an effective language condition policy. So in the end, the language condition policy is really good, even though the LLM performance may have been like some good, some bad, but the final language condition policy was only trained on expert trajectories, so it's really, effective. Okay, of course, the caveat here is that you have to have at least some success rate, and preferably it's like not really low success. So like at least maybe like 10% success rate would be a good number so that you can do this and you'll like collect successful trajectories in a timely fashion. But that highlights, I think this approach is actually very promising for mitigating a lot of the issues that we see with LLM powered systems. Yeah. Okay, so next slide.
I also agree that both sampling and like training on the success cases could help to improve like a baseline policy, provided you get the success cases. So
Yep.
it's also I've been thinking about this, like in order to get more success cases, it might be necessary to abstract your task into like higher and higher levels, whereby the number of steps needed maybe is lesser at the higher levels of planning. So you can get more success at each layer. So because if you were to do stuff like, your robot arm, you control the XYZ rotation of all the 6 degrees of freedom of the robot arm, I think it's very hard to like grab support from one side to another. The chance
Right.
of success is very low. But if you really fix certain actions, you might get greater chance of success.
Yeah.
And also your tasks could be more random. Like basically you don't have to have a very long task. You can have a short task also, so you can learn from those as well.
Yeah. And yeah, that's really correct. And we're going to see an example of that actually. Like how do you construct more and more complex tasks out of simple tasks in some of the following slides. So yeah, but really good point. Okay, so based on that high level perspective, how do LLMs fit into the robot learning pipeline? So here on the left is kind of an illustration of the robot learning pipeline. And there's a few components, like if you were to think about this from a reinforcement learning perspective, you have like things that are just about describing the current state and the task. So for example, the reward function is given the current state and the goal, and you just assign, a floating point number describing how much reward the agent has accrued in that particular time step. And on the right, there's more of a generative component where, say, if you had a planner or a policy, those things need to make decisions, they need to take actions. And so they're kind of generating trajectories, right, of actions. And also a world model which predicts future states is also a generative model of, the future state of the environment. So those are kind of harder, but we'll kind of see like how LLMs can be used to do a bunch of these things. I will focus on the high-level planner, the reward function, the policy, and the world model, not in that order, but those are the 4 kind of aspects that I've prepared to talk about today. And just bear in mind that when the LLM is only used for a particular component, it's the whole system that defines a policy. But you could have LLMs in multiple of these components. So like a lot of the things I talk about may be compatible with one another. Yeah. So, okay, next slide. Right. Okay. So let's talk about planning first. So what is a planner? A planner is, when you have the current state, choose an abstract action. Okay, so an abstract action is different from a low-level action. It's just a high-level description of what you intend to do next. So here you have robot observation, and the abstract action could be, for example, pick up the bowl. And people usually do use like language to describe such abstract actions because it's a very convenient modality for doing so. So this is valuable because it helps to decompose the learning problem and simplifies like the low-level policy learning subsequently. Like if your low-level policy knows it's just supposed to pick up the bowl, it's much easier to just learn to do that than it is to like try to figure out, figure out what it should do next and then like actually do the thing. It just has to learn to actually pick up the bowl. The second point is that the high-level plan is embodiment agnostic. So it doesn't matter whether it's a robot or a different kind of robot or a human. You can derive a high-level plan from all of these kinds of embodiments, and then the high-level plans more or less transfer to like different robots. Like any kind of grasper a robot that has a grasping capability will be able to execute like a plan to pick up the ball, for example. So that's two of the benefits of this approach. Next slide, please.
Yeah, sorry. On this point, I recently
Yeah.
read a book by Chip on how to
Hmm.
use the machine learning models
Chip
in
plan.
production.
Oh, yeah,
Yeah,
nice.
so there's one page in it that got me quite intrigued. It's saying that like TensorFlow, PyTorch, they are like high-level systems that can adapt to any kind of like compiler that you have, or CPU or GPU, because the instructions are high level, and later when it goes to a specific hardware, they will adapt accordingly. So it kind of seems that if you can do some form of high-level planning, you can avoid the complications of planning each and every single one endpoint that you're going. So it kind of looks very similar to what I see over here. You high-level plan, and then you will go to the robots in their own ways.
Yes. Yeah, essentially, that's kind of, that's the idea. Yeah.
Very cool.
Yeah. Okay, next slide. Yeah. So to illustrate this, let's do I'm going to do a case study on MindDojo. So MindDojo is this simulated environment based on Minecraft with thousands of language prompted tasks. Okay, just a show of hands in the participants. Who has played Minecraft before? You can raise your hand or put down your hand.
I've seen it before.
Okay. Who is familiar with Minecraft, shall we say? Um, all right, so 2 people. Okay, 3 people. All right, I'll just explain a bit about Minecraft then. So in Minecraft, you control this agent in this block-like world, and you go around the world, and there's lots of different things you can do, like crafting, fishing. You can build a house, you can fight enemies, etc. It's kind of this open world sandbox game where where the idea is you can just explore and do anything you want, and the environment supports that. Okay, so this environment is built on top of that and comes with a lot of different kinds of language prompted tasks, and some of these are actually very difficult. Like on the right here, we have 2 examples. One is fight an ender dragon. An ender dragon is kind of this like end game boss that's very difficult. You need a lot of good equipment, and also it's like not easy to find the boss in the first place, so you have to travel to a bunch of places. And the other thing is build a nether portal. So that also requires a lot of different kinds of advanced crafting material, and also the process to build the nether portal is like quite complicated. So yeah, these are just examples of difficult things that you can get robots, or you can try to get agents to do. And if you just started from a bottom-up way, like you just used reinforcement learning to try and do all these things, it would never work. It never work in 1,000 years.
Yeah, I
Okay,
like
so
that. Reinforcement learning is super slow to learn.
yeah. So okay, maybe this is a good time to look at the questions. Okay, so what is the difference between a physical robot and some other agent in Minecraft, like a digital? For the purpose of there are differences, but I'm going to ask you to just imagine that they're mostly similar for the moment. It's like, of course, the physical world is much more complicated, but Minecraft is still like complicated enough that we can use it as a good, microcosm of the challenges that we want to solve. Yeah. Next slide, please. Okay, so one way that LLMs are used to solve this is by defining policies as code. So code is convenient because an LLM can read and understand language, and code is a language. And also code is reusable. So you can define a code function that does something, like see here in the middle, it says combat zombie. And combat zombie is actually a function that's added to your library of functions or skills. And in the future, when you define a new function or skill, you can call zombie as a primitive. So that's one interesting takeaway from like how to use LLMs for such things. And this also extends to like real world cases with a bit more difficulty, because in this case your primitives can be like directly calling the Minecraft API, whereas in the real world you will need primitives that you create yourself. But given a sufficiently good set of primitives, an LLM can construct very complex behaviors out of that. Next slide, please. Okay, and what the LLM is also capable of doing in this environment is proposing interesting goals. So for this paper that I'm going to talk about, the high-level goal was to discover as many diverse things as possible. And this leverages the LLM's ability to decide, what is interesting and what is diverse. And crucially, what can I do next, given the current state? So if you're just starting out, you obviously can't immediately go fight the endgame boss. You have to do a bunch of other things first. And the LLM is capable of understanding this and sequencing the tasks in a reasonable way such that you can make progress effectively. And we can see here in diverse environments that the LLM can reason about immediately executable tasks. So if you happen to be near a river, you can do the task of catch a fish, for example. And if you're hungry, then you should focus on, getting food, and the task would be to kill a pig. Okay, next slide. Okay, a third interesting thing that I saw from this paper is using self-question and answering to elicit reasoning as well as grounding. So for reasoning, the self-QA forms a kind of chain of thought where by asking and answering questions to itself, it decomposes the thinking process and allows the LLM to reach a better conclusion than it would have if you just ask it the question directly. And so here we can see how to craft an iron pickaxe in Minecraft. And the LLM can also answer this question with a wiki lookup. So it has access to this Minecraft wiki. The wiki contains documents which are indexed by vector indexed database of documents, and the LLM is capable of looking up these queries to provide grounded information about the environment in order to make its decision. So it's not just imagining that you can do stuff with an iron pickaxe. It actually knows, or you can provide it with the raw information that is correct, that how do you craft an iron pickaxe, and then the LLM will be able to decide using that information what it needs to do next, make a crafting table, etc. Next slide, please. Okay, so putting all of these together, what that enables is open-ended learning of extremely complex behaviors. So this paper is called Voyager, and in the orange line that we see here, Voyager is able to acquire many kinds of diverse items and skills, outperforming all the other, all these other things are actually language model baselines that get stuck somewhere. But Voyager, by combining all these tools or these methods, is able to continually improve, and it doesn't plateau, which is interesting. A note here is that this whole system is LLM based. There's no downstream low-level RL policy here. It's just fully end-to-end LLM, and that's useful because if you were to have such a system that's capable of being deployed on robots, you wouldn't need the low-level skills. You could just, if your primitives are defined as code, then you could collect interesting data in the real world from scratch, or you have a starting point to bootstrap yourself into the chicken and egg problem that we talked about, and then you can collect data to train better policies and collect, use those policies to collect even more data, etc. Yeah.
Just a caveat, the from scratch is not exactly totally from scratch. They do have some primitive functions like how to do A-star search, how to shoot a creature. So all these are already predefined in code, and they can call at the beginning.
Right. Yes.
Because if you totally train from scratch, maybe LLMs cannot ground themselves well to the environment to generate the right code.
Yeah, that's a good point. So it's not totally from scratch, but it's still if you think about all this stuff that we're talking code, it's not things that you would be able to use in your policy anyway. It's very hard to propose a reasonable way to get a policy to understand how to use that kind of code. So I see this as a nice way to tap what would essentially be off limits to RL policy, for example. Yeah, next slide, please. Okay, and also the agent that is empowered by this system is able to explore a much wider range of environments, orange circle, than all the baselines. So it pretty much traverses like 2/3 of the world. And that's all from the high level goal of just discover as many diverse things as possible, which I find to be very interesting. It's like emergent high level behavior. Next slide, please. Okay, so that was kind of an end-to-end, LLM system, and one of the components of that was the LLM proposes interesting goals. So now let's look at that in isolation. So if an LLM can propose an interesting curricula, then you can use that curriculum as something that you use to train RL policies in sequence. So let's consider this now simplified Minecraft setting. So this is still Minecraft, but it's 2D and it's called Crafter. And the task is you want to learn as many different skills as possible. So there's these 15 tasks on the right. Possibly there are more, but let's just think about these 15. So you can do some subset of these tasks well. And then the LLM uses its notions of, semanticity to suggest like interesting tasks that can be done next. And this is both based on achievability and what is actually interesting in order to be able to do more of the tasks in the future. Right. Next slide, please. And we find that the curriculum based on interestingness outperforms the non-semantic methods. So this orange curve is the LLM curriculum, and the other two ones are, the blue one is a linear progression curriculum. So that's just like based on the task completion success rate. And if you have learned a task really well, then you move on to like a task with lower success rate, for example. So, but both of the baselines used here do not have this notion of semanticity, so they waste time on redundant tasks that do not actually expand the agent's skill set. So overall, the curriculum with interestingness, is more sample efficient. Next slide.
Sorry, I have a question here.
Oh yeah, sure.
How do they define interestingness?
Right. So it is just asking the LLM what is interesting.
So without any grounding or like two shot something? Or is this one?
Maybe, yeah. So I don't think there's a lot of prompt engineering, but I could be wrong. Yeah, I actually have like in my haste to make the slides, I've forgotten to put a lot of the links to the papers apparently, but I will.
No worries. I think what they prompt well here is not the interesting part, because interesting is kind of vague. They should define it more objectively, in my opinion. But I think what worked well here is they say you want to learn as many different skills as possible. So this kind of biases the output to be more diverse.
I see. Yeah.
I mean, the explore-exploit paradigm kind of works. So if you explore more, maybe you can learn more skills, but you kind of need to already have some baseline in order for this to work.
Yeah, that's fair. This paper is called, okay, after the talk, I will go back to the slides and I'll actually put in all the citations for all the things that I did. But that paper is called Omni, Open-endedness by Modeling Human Notions of Interestingness. Yeah, if anyone's interested. Okay, so I do like think it's interesting that LLM curriculums, because they're semantic, they outperform other kinds of curriculums. Next slide, please. Okay, so separate from curriculum learning is also the idea of planning over skills. And this is something that we saw in Voyager, and is something that has been applied to robotics. So on the left is possibly the first example of work that we have that demonstrates this. So in this case, the LLM is being grounded in what the robot can actually do. So let's say you have a query such as, I spilled my drink, can you help? And then just based on the text, the LLM can propose, a list of several things that would be plausible to do next. like find a cleaner or try using the vacuum. But those may be things that the robot can't do. So the robot then has to provide its own perspective, and you see that on the right with the value functions. The value functions say essentially determine what the robot thinks it's capable of doing. So the robot thinks it's capable of finding a sponge, for example. And then by integrating these two different sources of feedback, you get the final decision-making probability, final distribution over actions. And in this case, the highest element would be find a sponge. So that's something that both makes sense to do, like as the LLM thinks, and also something the robot thinks it can do. So that's why, so by combining these two, we get the overall decision-making process. Okay, and this is really interesting. This is quite powerful because it leverages the LLM as kind of a planner. And then you eliminate a lot of the difficulties of actual robot planning. Yeah. But one of the weaknesses was that this is, open loop. So there was no way to, say, provide feedback or adapt to a different environment. Let's say if you perturb it, you need to be able to prompt the LLM in some way to say, okay, well, now this has happened, etc. And that's the problem being solved on the right, where in this paper called Inner Monologue, we have closed loop planning, where you can actually tell the LLM something, and then the LLM, goes to do it, action go to table, and then actually it sees there's multiple decisions that it could make, and then it can come back to the user and ask, do you want water or Coke? And then you can tell it, and then etc. And also it can be robust to environment failure. So in this case, it tried to pick up the Coke can and it wasn't successful. Okay, then it doesn't normally if this was an open loop plan, it would continue to the next step, just bring you the thing, but it will actually not bring you anything because it's not holding anything. But in this case, it's able to recognize it hasn't been successful and then just tries to pick up the can again and keeps doing so until it's successful before executing the remaining steps of the plan. Yeah, next slide, please. Okay, so now we've seen how LLMs can plan over skills. But what about the cases where there are missing skills? Okay, so one really simple way, and I kind of like how simple this is just allow the LLM to ask for a new skill. So if it decides that it doesn't have a current skill, then you just include a primitive called learn skill that adds the skill to the skill library. In this paper called HELP, or Human Assisted Lifelong Learning, there's this, they allow the LLM to do this, and when the LLM calls learn skill, it prompts a human to collect demonstrations which are used to efficiently learn a policy for the skill. And then the LLM also receives a negative reward when it incorrectly tries to learn a skill, as in it already had the skill but it wanted to learn the same skill, for example, then it receives a negative reward. So it encourages the LLM not to just call this frivolously, for example. And this is a interesting way to try and expand the pool of available skills. Next slide, please. Sorry. Okay. Go back one slide. Just to talk about this a bit more. What I find to be useful about this is, if you were a human teleoperating data, now you can wait for the LLM to decide what it needs to do before you collect teleoperated data. So it's potentially more sample efficient and reduces the burden on you to collect data. So compare supervised learning and active learning. Active learning is proposed to be more sample efficient, and that's kind of the dynamic we're seeing here. Next slide, please.
Yeah, I'm just thinking, can you imagine a case where in the future the AI's only job for humans is, hey, give me a demonstration?
I've had this discussion with friends. Yeah, are we just going to be relegated to creativity machines, or actual demonstration machines for AIs in the future? That's possible. I don't know. It seems rather dystopian.
I mean, that's what OpenAI is doing. They recruit all programmers, come and do their programming stuff, fine tune on them. recruit creative writers, so
Yeah,
you provide the context for the machine learning to learn.
yeah, pretty much. Yeah.
And
Okay.
that was just a thought experiment. But
Yeah. But I think that's a good comment. Okay. Yeah, and the last point that we should touch on is what if in this process of generating a high-level plan with the LLM, you generate an infeasible plan? And here's an example in GPT where okay, you can take a minute or so to read the problem setup. So you have 5 blocks. Actually, there's a picture here that describes it way better. So you're trying to get from this block state to that block state, essentially. Um, okay, and then what does GPT ask you to do? So it says, okay, it outputs this, list sequence of commands, and you look at it, and actually you don't really understand it, right? Because it's just kind of in text. Next slide, please. Or rather, yeah, just click. Yeah, and actually you see that GPT at one point it says put B3 on B5, right? So that's correct. Okay, and then click again. But then it says put B2 on B5. So that's not possible because we've already put B3 on B5. So this wouldn't be obvious to you like a priori, but it turns out to be infeasible. And how do we like avoid such problems of infeasibility? There's many ways, but one of the nice ways that I've seen is just sidestep the problem and you outsource the reasoning to a planner. So there are like planning languages in robotics that are designed to solve this kind of task, and they have guarantees on correctness. So if the LLM can accurately translate your request into the format that the planner understands, and then the planner can give you the correct answer, and then LLM just has to translate it back to you in terms of language. So that's the approach taken in this paper called LLM plus P, which is where the P stands for planner. And on the left, you see like instead of trying to solve the problem, the large language model is asked to output a description of the problem in a planning domain definition language, PDDL. And this actually outperforms like all approaches that don't use a planner. Like you can see all the if you do tree of thoughts, that's the middle one, and versus if you do planning, tree of thoughts does horribly and the planning does really well. Caveat that this paper was at least 6 months ago, and GPT-4 may have improved since then, but I still think this is like quite a nice way to just avoid the problem of like hallucination. So now it may still hallucinate, but it will hallucinate at the level of translation, and at least you can check whether the generated description is correct, right? In terms of format. And translation is obviously easier than reasoning. Yeah, and it benefits from like having the guarantees of the PDDL, assuming that all the translation steps were correct. Okay, so next slide, please.
No, I just want to comment on this slide. So,
Yeah.
there's been a lot of talk saying that, LLMs can reason, LLMs can plan. I mean, when I did the 2D grid wall environment, I realized that they are at best pattern matches. Their planning is spurious. Like sometimes it gives you good
Yes.
results, sometimes it doesn't, like what you saw in the block example
Right.
earlier.
Yep.
Yeah. So I do agree that like there's a reasoning module that is lacking in large language models, planner module that is lacking. Tree of thoughts you can see in this paper, it still doesn't do well. So tree of thoughts is probably not the right way to plan. You don't plan with a LLM in a LLM calling an LLM and so on. You need some other way to plan that is more consistent, more rule-based, something like a planner here. So highlights that LLMs cannot work in isolation. It's best to delegate the right stuff to the right tools. Yeah, I think this is quite clear in this paper.
Yes, I agree. Yeah. Okay, so the overall takeaways from this brief survey of LLMs, excuse me, for planning. LLMs are useful because they propose semantically aware plans, like goals or curricula, which induce effective exploration. LLMs can also use tools like code descriptions or language descriptions of tools using those descriptions to infer what the tools mean, and then like using the tools effectively. And like learn a skill is also a tool, so you can ask for a new tool. Like it's a self-expanding system. Okay, and one of the issues is that hallucination, is still a problem when you ask an LLM to directly do planning. You don't have any guarantees there. But if you outsource this to something else, you can kind of sidestep that issue, I think. Yeah. Next slide, please. Okay, so now we're going to talk about reward functions. I do want to mention, like, the participants can feel free to just ask questions at any point if anything's confusing, because I recognize there's a lot of information to take in at once. Yeah, but let's move on to talk about reward functions. Okay, so a reward function is, given the current state, assigns a floating point number of the reward. So why would we want to do this? Well, evaluation is easier than generation. So if you just had to, look at the current state and decide whether something has happened or not, it's much easier than having to reason about future states, which is what you're doing when you're trying to output plans, right? It's also like more similar as a task to, say, visual question answering, which is something that we already train LLMs on and evaluate them on. So we expect LLMs to be better at this zero shot. And lastly, the rewards are also embodiment agnostic again, similar to high-level plans. If you have a reward function for a task like pick up the bowl, that's going to mostly be the same no matter what kind of robot or human that you have. Yeah. And in the case of like goals, you can also get the goals from a planner. So this fits into what we talked about previously. Next slide, please. Okay, so one way that LLMs can define reward functions is to write code that defines a reward function, and based on like a natural language description. So here are two works that try to do that. One is, and they're basically pretty similar. On the left, we have the language model taking in user feedback or user input. The user says, make the robot dog stand on 2 feet. And then the LLM translates this into a code description of that behavior. And then this is used together with, actually what's going on here is just MPC. The MPC optimizes this reward function, and you get a robot that stands on its 2 feet. So that's pretty cool. It would be very hard to just like analytically figure out, what the right reward function is for that, but LLM is able to do it. I should mention here that it's not quite as simple as this, because there is a interactive like step where the user has to say, oh, the robot's not standing up enough, or etc. But overall, this is the pipeline. You can get a pretty good reward function from user input. And on the right, we see here, instead of just configuring functions, LLMs are actually allowed to write its own functions. So based on an environment description, it can write code functions that parse the description and determine whether like tasks have been accomplished. And this generated reward is used for multiple kinds of tasks in MetaWorld, which is a multitask robot simulation environment. And the reward function coded by the LLM actually outperforms the Oracle reward. So Oracle reward is just something that humans came up with, and this reward function that LLMs wrote is just better. It allows policies to learn more sample efficiently, for example. So that's pretty cool. So LLMs can write code. Yeah. And next slide, please. And it works pretty well. Okay, so besides just writing code, LLMs can also do question answering. And question answering is interesting because it has been used as an objective, right? You can train an agent to collect trajectories such that the trajectories are informative enough for question answering. And that's the approach taken in this paper called Eager, where they define task-relevant questions with an LLM. So on the left, if the goal is to put the blue box next to the ball, then you generate questions. And then you try to answer the bunch of the questions using the agent's trajectory. And you reward the agent if it's correct. Yeah. And this incentivizes the agent to explore, to get more information. Sorry, there's a caveat here. These approaches where in this paper, the question generation and question answering is actually not done with an LLM, but you could use an LLM to do that, for example. Yeah. Next slide, please. And the takeaway from this paper is the semantic intrinsic reward, which is defined by question answering. That's the blue curve here. It outperforms lots of other kinds of intrinsic reward. So intrinsic reward is useful when you're in an environment and it has low or it has zero rewards most of the time, right? Like if you're in this agent, you have this agent in this environment and you're just taking actions, and most of the time what you get back is zero reward. So you don't have any basis to compare like which action is better than which other action. But intrinsic reward allows you to coherently, converge towards good behavior that will eventually let you get like positive reward. So it simplifies the exploration problem, and that's what all the intrinsic reward methods are trying to solve. And in this case, the proposed intrinsic reward based on question answering, which is eager, outperforms all the other kinds of intrinsic reward for allowing like exploratory behavior. Yeah. Next slide, please. Okay, and the last way that we could think about using LLMs for reward functions is just to re-annotate prior data. So let's say you already have a bunch of demonstrations which are collected for some other task, right? And a common idea in reinforcement learning is called hindsight relabeling, where there was a task that the agent was trying to achieve at the start of the episode. The agent did something during the episode, and then at the end, what is actually achieved may be different from what they were trying to achieve. So hindsight relabeling is just the idea of taking what was actually achieved and setting that to be, the description for that episode, for example. And this is something that LLM can do. In this case, they used a combination. Okay, actually, they just use clip. They use clip to annotate a data set of demonstrations with like the goal that was actually achieved. So maybe the agent here was trying to grasp the blue object, but what actually happened was like in some of the frames, the agent is grasping the red object. And so you can re-annotate those frames to say agent is grasping the red object. And then now the LLM, or rather now the agent knows how to grasp the red object, or it has seen examples where it has already grasped the red object, for example. And re-annotating the data in this way improves the sample efficiency of learning. Note that these are all like separate policies trained from scratch on different tasks, but they're reusing the data from the previous tasks. So by reusing data and re-annotating it for the current task, you can improve sample efficiency. And this can obviously be combined with like other methods that also, reuse the policy.
Just a point on this. I like the idea of learning from arbitrary goals. So that means even you don't hit your original goal, you learn from what you have achieved so far. So this method has also been used in hindsight experience replay, where basically like in deep Q networks, basically Q learning, they just take where the agent reach as the end goal, all right, and then they just train that as if that's the goal. So you can essentially learn from any trajectory that you have because of this. In fact, this is also what I did for fast and slow, learning fast and slow, because you can learn from any start state to any goal state, and you learn the output action. So I find that this in general, this way of goal-directed learning, it's way more efficient than reward-based methods, including the intrinsic reward-based methods. Because I actually spent 4 years going through all these methods you were talking about, like value-based,
interesting.
rewards,
Okay.
and then finally the last method I came up with is learning fast and slow. So
cool.
all right, So
Very
just to
nice.
let people know that this arbitrary goal method of learning is very efficient.
All right, awesome. Okay, yeah. And moving on to the next slide. So our takeaways here are, this is just a survey of like how LLMs are used to do rewards. So they can translate, language descriptions of goals to actually like code functions that check for those goals. They can propose semantic intrinsic rewards for exploration, and they can allow you to repurpose existing data for new tasks. So which one of these is best? Some people have an opinion, and John surely argues for the repurposing existing data. I think the jury's out, but we'll see what happens we'll see what happens in this space. Yeah. Next slide. Yeah, and now a note on like zero-shot versus fine-tuned performance. So currently we've talked about high-level planning and reward functions. Those can largely be obtained zero-shot. But because that's because they are using some kind of high-level information, or they don't need to concern themselves with low-level robot information. So, but in the next sections, we'll see that you actually need to fine-tune the LLM a bit because they involve like low-level robot state, for example. Yeah, and that's like trickier to set up, but I think it is the direction that robotics will eventually converge to. Next slide, please. Okay, so now we can talk about world models. So what are world models? Given the current state, you would like to predict the future state conditioned on the action that you're taking. So here, if the task is like pick up the banana or put the banana in the bowl, or rather if the robot is taking that action, and then you would predict that the future observation is that the banana is in the bowl, right? And this is valuable because in particular for an LLM, an LLM can not only use like the robot's observation to predict the future state, it can also use language as prior knowledge about what could possibly happen in the future state. Right. In this case, the LLM may know that like if you drop the banana, it will fall. So it could, instead of like moving the arm all the way into the bowl to put the banana there, it might just like drop it from a certain height, for example. And also the world model is task agnostic. So it's not embodiment agnostic anymore. It's still, in this case, it's kind of specific to the robot, but it can be used for like many different kinds of tasks. Next slide, please. Okay, so just a primer on world models as they are used in robotics. So the basic idea is a recurrent model where you have an encoder and decoder for the state. So the step to run inference on a world model is to encode the observation to a latent state. And then this latent state is used to like predict the future latent state given the current action. And then to train this world model, you decode the future latent state to the future observation, and you can train on that like prediction with reconstruction loss. Okay, and to oversimplify, this architecture of world models called Dreamer v3 is state-of-the-art reinforcement learning, a model-based reinforcement learning approach in many domains, including locomotion, Atari, Minecraft, which we've talked about, etc. Okay, so and then the question that we can ask is, what if we just add language to this, right? If we just have an LLM that can do this. And that's the next slide, please. So that's the concept explored in this paper, Dino Lang, fine-tuning a world model with and what they try to do is fine-tune a world model with an LLM objective. So now instead of just encoding, the robot camera feed, you also have a language description, and you tokenize the language, and you try to predict the next token as well at every step. So yeah, essentially it's the same. You still encode the current observation plus language, then you predict the future latent given the action, and then you decode the future latent to the next observation plus the next language token. So what is interesting about this is that it's a joint architecture for, say, video prediction and language modeling, which can be pre-trained on either of these modalities alone. And in the paper, they show signs of positive transfer between modalities, in the sense that if you pre-train on just language, and then you subsequently have joint training, the pre-trained model does better than learning from scratch. So you actually learn to model the world faster. Next slide, please. Okay, so what this allows you to do is actually use language to predict the future. So for example, if you have a language, so consider this like game-like environment where you control this agent in, what's a simplified house, and then you have various kinds of household tasks, like pick up the bottle. Okay, so some kinds of language are useful for predicting future states, such as the bottle is in the living room. This tells you that if you go into the living room, you're likely to find the bottle. So that is, or you're likely to see a bottle in the living room. So that helps you predict a future state, right? Like a future state of you being in the living room and seeing a bottle. And the other kind is task relevant, where if the task is get the bottle, that helps you predict a future reward. So you know that in the future, if you pick up the bottle, you get a +1 reward, for example. So using diverse language descriptions like this is kind of the central question of this paper. And next slide, please. Yeah, and also using the past to predict language tokens. So if you have, for example, a video of you, a video trajectory of yourself that's been encoded through the world model, and then you're asked the plates are in the blank. Based on the agent's prior knowledge, you can figure out that the plates are actually in the kitchen because it saw the plates in the kitchen at some point. Next slide, please. Okay, and the key here, I think, that is interesting is when you train a world model with language in this way, it benefits from diverse language hints. So they compared 4 setups where different kinds of language are provided. So here are 3. Okay, so in all cases, you always tell the agent what it's supposed to do. That's the task. And then in 3 of the other cases, you also provide a different kind of language hint, where in the second one, you say the bottle is in the living room. So that tells you about the future state. In the third one, it's a correction. So you can tell the agent it's supposed to go the other way. And the fourth one is if you step on the pedal, the bin opens. So that's like telling you what happens if you take a particular action. And the punchline here is when this like combined world model and language model can incorporate all these diverse kinds of language hint to improve its modeling of future states. As you can see, compared to like the task-only performance, the score improves. Next slide, please.
Actually, I'm just curious. In this case, did they train the world model from scratch, or is it a pre-trained? Like
it is trained from scratch. Yeah.
So it takes a lot of samples to train, right, for this?
Yeah, a fair number, quite a lot of samples.
Yeah. So this is the problem with world models. The other thing that I have is, did they store the past history as pictures or as text? Like it seems that over here, like this.
Right. So you don't actually need to store it. It's just like what happens if your agent experiences this trajectory, right? So this is more like saying the agent has experienced this trajectory, and then because the world model is recurrent, so the full history has been encoded in the recurrent state, and then the world model kind of knows like what happened in the past, so it's able to like use that knowledge to make a prediction.
Is it like an RNN kind of architecture?
Yes, yeah, it's exactly the latent state model is an RNN. So yeah.
RNN, the recursive neural network, recurrent neural network. This recurrent neural network has a vector of memory whereby it passes through a state, and I guess if they use transformers, it will remember more because the memory won't be as squashed up. One of the problems with RNN is that the memory itself keeps getting like overwritten as you go down the time steps.
Yep.
Another thing I think they could have added to this architecture is that they could have text-based memory, something like the generative agents paper. You could say at time step 0, agent went to living room. At time step 1, agent. You can store stuff in text, and then maybe
Mhm.
like retrieve the relevant parts to answer the question.
Right.
Yeah.
Yeah.
So yeah, this would help to reduce the memory loss,
Yeah.
especially
Yeah.
if you compress it like that.
Okay. Yeah. 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 So definitely, I think transformer architecture is an interesting thing to explore with like world models. Okay. So next slide, please. Um, right. Okay, so in the interest of time, I'm going to summarize the rest of this section. Basically, the idea here is that you can like once you have an LLM that accepts both robot states and language, you can use the prior text knowledge. You can pre-train on like prior text knowledge to improve subsequent world modeling performance. Next slide, please. And the model benefits from general pre-training. So when I say general, I mean like text that is not relevant to the domain, whereas in-domain pre-training is text that is highly relevant to the domain. And you can see in this plot that the general pre-training, similar to like pre-training on, say, internet text, for example, it does better than in-domain pre-training. So the purple line here does better than the blue line or dark green line. Yeah. And I find that interesting because it means we have like science of life for scaling this up to like better data sets and environments. Okay, next slide. Yeah, and the other way in which I've seen LLMs be used for world models is to translate to a probabilistic program. So it's the same idea before as like outsourcing, your reasoning to a different dedicated module. And in this case, it's like you're outsourcing the world model to a dedicated generative model, like a probabilistic program. Okay, I'm going to skip the example again because it's a bit wordy. But yeah, next slide, please. But the key idea is that the language model can translate this natural language query into a query over a probabilistic program to do inference. So if you wanted to ask like a question, if you gave the LLM some information like Josh won against, like, consider this tug of war environment, and then like player Josh won against Leo, and then like Josh won against Alex, and then like Leo and Alex could not beat Josh, and then how strong is Josh? So you could ask the LLM to answer that question directly, or the approach taken in this paper is to translate the information into like a structured probabilistic program format, and then do inference over the probabilistic program to answer the query. Yeah, and that actually allows it to explicitly model the data generating process, which some people already hypothesize the LLMs do. Yeah. Next slide, please.
All these are NeurIPS papers, right? That last year NeurIPS.
I'm not sure. This is like actually quite recent. This is from this year. I don't know if it's at
I saw
NeurIPS.
something similar NeurIPS last year, but yeah,
Oh,
please continue.
cool. Yeah. Yeah. So the takeaways from that are like, language is a really interesting modality to try to inform, say, predictive models in RL. And I think it's a very exciting direction for our future work. Because we do have a bunch of prior knowledge about the world just encoded in language, and how do we try to embed this prior knowledge into our agents? And that's like LLMs are one way that we could do that. Next slide, please. Okay, and then I think that now we're building up to like finally, how do we use LLMs to directly get the policy? Like this is in some sense like what we want. All the other approaches are kind of you get the LLM to do this, and then you can get a policy from that. But this is just, you have the LLM and it directly defines a policy. So there's nothing else in the pipeline. It's just exactly what you want in order to take interesting decisions in the world. Next slide, please. And the overall idea here is simply think of robot actions as another modality, right? LLMs are really good at translating between languages. So robot actions are a language, and you can translate between language and robot actions, or you can translate between text and robot actions as languages. So that's what this paper does. It's called Motion GPT, and they simply fine-tune an LLM to directly output like low-level actions in the form of a motion trajectory. And at test time, the LLM can robustly answer motion text queries. So you can see in the example, can you generate a motion that a person kneeling on the ground gets up? And then they actually do have the motion starting in the kneeling position and then slowly getting up to a standing position, for example. And then you can also do like so that was text to motion, and you can also do like motion to text. On the right, you can see that there was this motion trajectory, and then the LLM was able to describe that in text, for example. Okay. Next slide, please. And scaling up this paradigm is what gets us to RT2, which I consider to be like one of the most impressive robotics works recently, or perhaps ever, because what they essentially did is take a LLM which is pre-trained on internet vision and language data. See on the left, we have this internet scale VQA and robot actions. So the LLM actually understands all of these different modalities, images, text, and robot actions. And then the LLM is directly fine-tuned for robot control, unlike a robot dataset. So we have like complex queries here, like what should a robot do to execute this task? And then like the answer would be some kind of robot action. And the LLM is fine-tuned with like this imitation learning objective on expert trajectories. And this kind of general recipe results in a generalizable instruction following policy, RT2. I highly recommend people to read this paper because the results demonstrated there are like super impressive. And this is kind of what convinced me that training LLMs end to end to just be the policy is like the eventual direction that robotics will go in. Yeah, next slide, please. And it's just a question of how we get the data to do that. Okay, so some examples of the capabilities are complex manipulation reasoning tasks. So these are not just like picking up a specific object. First, you have to reason about what object to pick up. Like here, there's examples where move banana to Germany in the middle there, for example. And this requires the LLM to recognize the German flag. And in the bottom left, there's move the Coke can to Taylor Swift. And it has to recognize Taylor Swift, etc. Okay, there's a lot of stuff here. I'll move on in the interest of time. Next slide, please. And this generalizes really well to diverse environments. So yeah, unseen objects, unseen backgrounds, and unseen environments, it works across all of this. And that's because of the pre-training on diverse internet data. Next slide, please. Okay, and the takeaways here are that robot actions are just another modality that you can use, and LLMs pre-trained on internet data can be fine-tuned as policies. This allows them to scale to like extremely complicated tasks that involve complex visual reasoning. Some of those are actually like also quite long horizon, so they involve multiple sub-steps that they would have to execute. And because they pre-train on like internet data, they have like massive generalization capabilities. So I see this as what robotics is going to do in the future, or the most promising thing that robotics can do is try to take LLMs that are pre-trained on internet data and you fine-tune them on robot data. And if we have like really good robot data, it will be even better for such LLMs.
Now, while you say that this is a breakthrough, I think this is disappointing that the community is headed in this direction.
Okay.
Storing data is a problem. Right. In other words, you say end-to-end LLM learning is all from massive amounts of data.
Yep.
And I mean, even you look at the model here, like the output is in action space, which could be
Yes.
very low dimensional. And then like there should be some form of hierarchy in between. Right? If you just do tokens like that, there's a very high chance of of not being able to get it out. Because
Yeah,
did they do like chain of thought? Like for example, move
no,
my left arm, then from move my left arm generate these actions. Did they
no,
do
it's
something?
just directly fine-tuned to do stuff.
I think this will be hard to generalize, in my
Okay,
honest opinion. Yeah,
that's fair. Yeah.
yeah.
Is definitely like the most, say, simple recipe that we have for like a generalist robot, and there could be like other more complex recipes, but this recipe has been shown to scale with
With
data,
data,
and
by throwing data at the problem, yes.
yeah,
I,
yeah.
I
So,
mean,
you know,
yeah, same.
so yeah, bitter lesson, right? If you know, general methods that scale with compute that are likely to outperform, uh, you know, more like expertly designed methods. Yeah, but yeah, it's totally fair to say that this is, you know, simplistic, and obviously people may come up with more principled things in the future. Okay, yeah, next slide, please. And maybe to connect this back to what we were talking about earlier. So we were considering how to connect LLMs to robots for decision making. Next slide, please. And the solution may be that we just don't need this like middle layer, right? That we just don't need intentions at all. And we just train end to end on the whole thing. It's like that's the most simple thing you can do, and it works somehow. So yeah, next slide, please. Okay, I have massively overran my estimate for how long the previous section would take, but now we finally get to the examples of what I did in MiniGrid. Okay, yeah,
Oh yeah, by the way, don't
so,
need to rush it. It's okay. I think I'm okay to stay a little longer. Just
oh,
because
okay,
this mini grid is very interesting. So this
okay,
is
okay,
the reason why I wanted you to present, because
right,
this is something about how the agents can like learn how to do the
yeah,
thing on its own. Yep. So they'll be
fair
interesting.
enough. Okay, well, yeah, no, there's not a ton to go over, but yes, I hope that it's interesting to you. So yeah, so next slide. Okay, so first, what is the mini-grid environment? It's just a simple game-like environment where you have an agent. This is a red triangle, and there are some objects in the environment split into rooms, and the agent is given a task described in language, such as pick up the blue box, and it has to learn how to do this. So yeah, this is the setup, and the agent has simple actions such as turn left, turn right, move forward, etc. And it can also interact with objects, like it can pick up objects and open doors. Next slide. Okay, so so to solve this task, I was interested in doing LLM to decompose the high-level task into a bunch of low-level tasks and use that to accelerate learning. Okay, so as a baseline for that, let's see what happens when you have like manual decomposition. So if you already know the task and you already know like what are all the steps that you need to do, then does training the agent on that, you know, allow you to solve the task. So that's the setup that we consider here. Click, please. And so for this task of like agents of pick up the blue box, we have defined intermediate objectives, such as the agent is next to the key, agent is carrying the key, agent is okay, etc. These are all like fairly short horizon things that the agent needs to do to progress to the next thing. And click please. And we have reward functions for each of these that are like manually coded. So I wrote code that checks if the agent is carrying a key, for example, etc. And yeah, as a baseline. Click please.
Yeah, no worries. You can always replace that with LLM generate
Yeah, yeah,
reward function.
right. Yeah. So an interesting comparison that we can make here is firstly whether the agent sees the goal. Like, do you tell the agent it's supposed to pick up the key, or is the agent like does it see the intermediate goal rather? So we compare the case where the agent always just sees the high level goal and pick up the blue box, and the case where the agent sees like the intermediate goal, which is you know, agent is carrying key. Click please. And we also compare, you know, whether we need the reward shaped. We need the reward shaping or not. So we have all these reward functions for the intermediate objectives, and if we use them, then that defines like a denser reward. So the agent just gets +1 whenever it does any of this intermediate stuff. And the baseline is just the agent gets +1 only when it finishes the overall task. Okay, so that's the setup here, and I'm going to talk about like the results from this. Next slide. Okay, so comparing these like settings, on the left, the conclusion here is only the reward shaping is necessary. The maximum possible reward that you can get with reward shaping is 7, and the agent that observed the goal was able to, get to the 7, it was able to fully solve the task essentially. And actually, even like the agent that didn't observe, the intermediate goals, it still did pretty well, but it didn't solve the task. Yeah, and we did train this with PPO. Yeah. So, okay, and then on the right, if we look at the sample efficiency curve or the training curve, we can see that so this light blue thing is when the agent both observes the intermediate objectives and has the shaped reward. And this is the best setting. And this this green setting is when it has the shaped reward, but it doesn't observe the intermediate goal. So that is significantly worse. And then all the other ones like don't work at all. So so we have validated. So through this like initial thing, we validated that firstly the curriculum is necessary for this task, and secondly that the goal is like kind of necessary.
See, you have discovered what I discovered as well. Reward is not good. Goal-directed learning is better. Right.
Fair enough. Yeah. Next slide, please. Okay, so based on that, we can now like kind of propose our method to use an LLM for like many of these things. So we have a base RL loop where the policy takes actions in the environment and gets feedback. Okay, and click please. And then we can now define, and then the environment gives you an overall task. Click please. So we can define LLM decompose. Click please, which gives you, from the overall task, you try to get the intermediate objectives. So that's the first part of the pipeline. Click please. And again. And we also have LLM evaluate, which takes the intermediate objectives and writes, code. So basically, I'm trying to automate the two things that I was doing by myself manually. One was decomposing the task, and one was writing the reward function. Click please. And this feeds back into the policy. So this is how we propose to use LLMs in this setting. Next slide, please. Okay, so for LLM decompose, well, I don't know if this is actually that interesting, but I'll go into the details of the prompt strategy that we use. It's definitely not the best thing that you could do, I think. It's just something very simple intended.
It's great actually. The way you do the prompt, like you give the action space, right? It's like giving a layer of abstraction. You don't have, the agent doesn't need the fine-tuned example of the output state, like the RT2. You don't have to go into like the value of your sensory motor output. You can just give a broad output and the robot can execute step by step. So I like this approach, like way better than like RL-based approaches.
Okay.
You can continue, yeah.
Cool. So so here the objective is to get the LLM to output a reasonable plan for like solving the high level task. And we first describe, the basic rules on MiniGrid, as well as the current state. Click please. And we also have like rules, and we did a bit of prompt engineering, where the rules are essentially telling the agent only to use like static information to define the intermediate state. So we don't want it to, so we want because we want these intermediate states to be easily, evaluatable from a single observation. So we had to explicitly tell the LLM, you can only use like static information, for example. And the purple parts describe like the prompt engineering things that we did, where we've implemented a kind of chain of thought where we allowed the LLM to, have output its thoughts. So this is similar to React, if you're familiar with that. and you can essentially have any number of thoughts until it outputs its objectives. And we also had like a few examples of objectives. Yeah, and there's
Yeah.
a full prompt.
Just for those who are not familiar with React is like you have an observation, you have a thought, then you have an action. So like from the large language model in this tree kind of you can repeat this in a loop to keep getting your actions. One thing I have here is there memory in your system?
No.
So
So when you say memory, you mean like the agent memory or the LLM memory?
LLM memory, like what has the agent done in the past,
Oh,
whether
right. Yeah.
it's
No,
successful
no,
or
there
not.
isn't.
So it's
Yeah.
purely a semantic matching of the task to the action space.
Yes. Yeah. So I think memory was something that we considered, but we didn't get to that point. I still think it's quite interesting, like,
Yeah, it's a
because
pity because memory is like kind of my key focus right now. I think
okay.
the key to
Interesting.
solving
Yeah.
intelligence is to solve memory
Right.
because you can learn very fast with memory.
Yeah, okay. I would be interested to, redo some of this stuff with like memory aware LLMs. We can talk more about that offline maybe.
Yeah, of course, of course.
Cool. Yeah. So this is the prompt that we constructed. Next slide, please. And what it gives us pretty reasonable results for like both the task that we described just now and a more complicated task. So in the first one, it was like kind of a 6-step process, so 6 intermediate objectives plus the last one. And in the second case, it's like 11 intermediate objectives plus the last one. Okay, so that looks pretty good. And now we have to move on to writing the reward functions. Next slide, please. So the prompt strategy is pretty similar to the past, except that when we're doing this prompt, we start from the point of the chat history that already has the decomposition. So we included all the information previously at the start of the prompt or in the message history, and then now we ask the agent, or now we ask the LLM to like write the reward function for some part of its for one of those objectives. So we still have the instructions, which are some mostly about formatting and like telling the agent how to structure the function. Like it must be callable with a single argument, which is the observation, and returns a boolean, etc. And for formatting reasons, just have Python code block. I'm sure there's more principal things you can do here, like strict JSON or something. But yeah, that's the overall idea. And we also did like a bit of prompt engineering where the chain of thought is now encoded in the form of asking the LLM to explain its thought process in the comment. That seems to serve the same purpose of like getting it to think about what it should do. And then there are a few short examples of like what an observation looks like, and an example for the state agent is next to the red box. And you can see the full prompt in this like paste bin link. Okay, next slide, please. Okay, so just to show you what it looks like. Yeah, this is an example of the kind of function that we get. And you can see that it's actually like really simple. Like so this is to check if the agent is in the room with a purple box, and it says, is the purple box, if the purple box is in the field of view, then you return true, otherwise we return false. And that's like reasonable because as soon as the agent sees, the purple box, that it's in the room with the purple box. So this is a sufficient condition. It is not a necessary condition, but it's a sufficient condition, is the point that I wanted to make here. Okay, yeah. And yeah, next slide, please. Yeah, and now we can think about evaluating this on difficult environments. So when we actually do this like LLM pipeline, and we train the agents with the reward shaping using PPO, what we found is that, there are like signs of life in that the agent, when you provide like the LLM decomposition and reward, it learned to complete the task on the 7-step environment. So the simpler one that we considered, you can see on the left here that it achieved like a success rate of 1. So that's good. It learned that task. However, for the more complicated environment, it failed. So that would be like the lighter green curve that you see on the right. And you see that it fails because it gets up to maybe the intermediate steps, and it doesn't it doesn't seem to be able to progress beyond that. Yes, so that's the one. And in theory, if it solved the task, it would reach like 11 reward, like average reward of 11, but it didn't manage to do that. Yeah. So
Also,
this
your
is
reward
possible.
is not a 0-1 binary reward. You have intermediate rewards for every step completed.
So yes, well, the intermediate rewards are like 0-1 rewards, but yeah, there are like multiple of those in the episode. So actually, if it's an 11, if there are 11 objectives and each one of those has a 0-1 reward, and then you get 11, a reward of 11 if you do the whole task.
Well, that's a smart way to do it because PPO is being model free. It
Yeah.
kind of is very hard to learn all these specific steps. If you give it only reward after it completes 7 steps, the chance of success is very low. So having these intermediate rewards is key to get traditional RL methods to work.
Right.
However, I think if you just do away with PPO and just use the large language model directly, you may not even need the rewards. In fact,
Oh,
there's no
okay.
condition the action.
Interesting. Okay.
You just give the goal, give your current
Right.
state, ask for next action.
Yeah, yeah, I can see that. I think one of the motivations of this project was that we are actually focusing on, that last layer, right? Like, how do you map low-level intentions to actions, and how do you do that? How do you learn that mapping in a sample efficient way? So, we are thinking that, in the general case where you have a LM controlling a robot, it like you won't have, say, abstract actions that you can just ask the LLM to take directly in the world. You would need, a RL policy at the last layer. But how do you get as close as possible to, say, the low-level actions? And it would just be like the low-level intentions. And if you can learn that really sample efficiently, then the other steps can all be automated with an LLM. So yeah, I think in that setting we do need like the neural net. But yeah, what you're saying is also valid, where if you just wanted to use an LLM to do this directly, you could probably, get really good results. And if that's like allowed by your environment, that's like probably something better to try.
Yeah, interesting. This actually brings a point. If you want to use baseline RL right at the bottom, which I don't deny is useful, because sometimes you can't use language to ground your action. Like how do I say
Right.
move my finger up like that, right? It's very difficult to say move up 32 degrees, apply a force of 5 newtons. It's a bit hard to say stuff like that. How do we ground this or how do we train this RL model at the bottom? I mean, at the bottom maybe RL is fine. But the thing is, if you want to use like your experiences in life to like train this, I'm just thinking whether or not you really need RL also, because can you just do goal directed learning even at the bottom?
Yeah, I think it is like quite possible. It's just a question of whether it's more convenient to describe your task through a goal or through a reward, right? Some tasks can be described well through goals and some can't really. And like locomotion has not progressed to describing things in terms of goals because the intermediate trajectory matters. Like yeah, but yeah, I think that's an interesting point that generally is true for like manipulation kinds of things, right? You can't actually describe the task in terms of goal.
Yeah, I mean, food for
But
thought. I mean, we don't have the answer to this.
yeah.
I mean, RL-based methods are still pretty much the dominant methods for robots. So I
Yeah.
understand why you are using PPO, and PPO
Yeah.
is one of the more
Uh,
performant ones, and
Yeah.
PPO is one of the more performant ones.
Yep.
Yeah, it's just getting all these episodes out and getting the reward. There's a lot of reward hacking and everything. Yeah, I
Hmm.
mean, you don't give intermediate rewards or intrinsic rewards, it may not work. Yeah,
Yeah.
so rewards have its problems. A goal, I also agree that if you specify by goals, sometimes it's a bit hard to specify the goal. Like, how do you say that the arm at this position is your goal, you know? Yeah, but I mean, I guess if you represent it at different levels of abstraction space, like your hand position can be a goal. I mean, so you can probably express this at the lowest level, even as a goal.
Okay. Yeah. 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 I could see that. Yeah.
Yeah. Okay. Anyway, yeah. Let's move on. Yeah. This is just some thoughts that I have there.
Right. Yeah. Great discussion. And okay, so overall what we get out of this is it it works on the most basic level, but probably because a lot of the stuff that we did is highly simplistic, we didn't get it to scale. So I still think like you can like do this in a scalable way. It's just like we like firstly the choice of curriculum that or the way that we use the intermediate rewards is kind of um it's unclear whether that actually works in principle, because you could argue that the intermediate rewards are like distracting the LLM from actually completing the task. So maybe what you should do instead is just like use the data collected by the policy to train on like the end-to-end task where you don't have the intermediate rewards, so you don't have this problem of reward hacking, for example. Um, and yeah, but we didn't take it to that point, partially because we saw like there's other work that's already been done on this.
Or you
Uh,
could use goal-directed learning.
oh yeah, okay. Oh
Yeah.
yeah. All right. Um, yeah, I will talk to you more about that afterwards. Okay, so next slide, please. Yeah, okay, so that's kind of the summary of like what I did in MiniGrid. I would say that the main challenges were just we spent a bunch of time on like designing the prompt and getting the LLM to understand the MiniGrid environment. Sometimes was challenging. These days I think there's better way to design the prompts, like people have this automated prompt tuning methods, which I think could be useful. As I said, the curriculum that we use is probably not very good, and you could try to replace that with something better. And it will be interesting to like just try this with maybe a better or a visually aware base model, which may be able to you know understand things more directly without us having to code the text description pipeline as well. Yeah, but that's like an internet example of the LLM planning plus evaluation pipeline being kind of successful in MiniGrid. Okay, and yeah, in terms of future work, so this is like stuff that I think uh could be done in the space of LLMs plus robotics. So if we do a high level summary of like what was valuable in the past, we see that LLMs are useful for their semanticity and common sense, for like defining reasonable things to do. They're also useful as like a glue between modules. Like you can have LLMs translate between user feedback and code, and LLMs can can translate natural language to particular formatted things that dedicated specialized modules need to understand, and then translate back into natural language, for example. And LLMs are also like able to robustly incorporate user feedback. So if the LLM outputs a plan that you didn't like, you can tell it to change the plan a little bit, and it will be able to do that. The weaknesses are kind of twofold. One is hallucination. We saw this in the high level planning example. So this is kind of a fundamental issue with LLMs, but has been resolved in the past by, say, outsourcing the reasoning to a different specialized module. And the other issue is grounding. So what grounding means is, does the LLM understand like what it's seeing, or is it grounded in the specific environment that it's in? And it's questionable whether current LLMs really do that, but we would expect this to like get resolved in the future as LLMs become fine-tuned on robot data or pre-trained on robot data, for example. Okay, so one thing that I think could be interesting for future work is robotics-oriented LLM evaluation suites. So mainly data sets, benchmarks, and checkpoints that are, focusing on embodied decision-making capabilities. So we've covered like 4 ways in which LLMs are used in robotics, and all of these could be like valuable for LLM evals. Yeah. So like planning, reward function, reward model, and policy, all those. Well, policy is probably like the most like end-to-end one, but all the others are like good ways to get insights into potential failure modes of the LLM when used in such ways. Next slide, please. And I just want to cover a couple of recent works that try to do this. One came out very recently. It's a data set for evaluating LLM's reasoning on object physical attributes, and which is generated from a ground truth like object annotated data set. So a 3D object data set that has all the ground truth annotations, and then they process this to form a question answering evaluation that you can see here. Next slide, please. And the punchline is kind of although existing zero-shot model performance is lacking, like GPT-4, it only achieves about 50%. This is what inter-annotator agreement. Or 50% accuracy, whereas humans, after with multiple annotators agreeing on the same output, they achieve 85%-ish. So the best models lag behind like human performance, but the performance improves with fine-tuning. So that's like an example of a valuable eval, I think. Next slide, please. And another interesting eval is like evaluating the embodied decision-making process as a whole. So this paper is called VIMA. And what they have is like a data set of, vision and language, plus robot motion queries. Sorry, no, there's no robot motion queries. It's just vision and language. And just like evaluating the robot's ability or the LLM's ability to understand like what it should do to respond to the query correctly, which I think is valuable. And the nice thing about this is it's connected to a simulation benchmark, so that is actually like grounded in the environment. Okay, next slide. Another interesting direction, I think, is this trustworthiness. So given that we're going to try to use LLMs to power a lot of robotic systems, can we try to understand what the LLM is thinking? And I'm inspired by recent work that shows that LLMs learn emergent linear representations. So if you look at the activation space of LLMs, it's one view is that you can't interpret that at all. And another view, which has gained traction recently, is that you can actually like look at the activation, like the residual stream, for example, of transformers, and find structure within this representation space. And recent work has shown that LLMs do learn, say, linear representations of several things like the Othello board state in the case of an LLM trained entirely on Othello tokens. LLMs learn representations of space and time of like various locations or like events, and they form a coherent, organized structure in representation space, and also like even more abstract concepts like honesty, where there's a particular direction associated with being more honest or less honest, and you can like artificially stimulate or suppress that direction to make the model's output more or less honest, similar to neuroscience. So it's interesting to think about whether these ideas translate to robotics? Like, do LLMs learn representations of object physical attributes, for example, or their goals that they have to be taking, or like whether their plans are feasible, etc. And also like whether we can control LLM behavior by intervening on those representations. Okay, and next slide. And the last thing that I think it would be interesting to try in this space is just fine-tuning LLMs with RL. John is probably not going to like this, but the motivation is currently
Don't worry,
our
just
best.
go ahead.
Yeah.
Please say what you
Cur- yeah. So currently our best models are pre-trained on internet and then trained with imitation learning, right? And you think of the analogy to actual LLM training, is like pre-training on internet text, and then like you have these instruction following fine-tuning data sets. That's exactly what is happening in robotics right now. But in LLM space, they also have a final step of RLHF. And in robotic space, we could also do that. Like in fact, we can do it better because when we have a robotic environment, we have a ground truth reward. Whereas in like RLHF, it's kind of this like they have to jump through a lot of hoops to try to construct the reward function from human preferences. But in robotics, we just have like good reward functions that we can use already. So I haven't seen anyone do this, and maybe it I don't know if there's some like hidden flaw with this line of reasoning, but it seems that if you just take LLMs and try to fine-tune them on robot RL tasks, it would be a reasonable extension of like the LLM as policy approaches, where they're just taking an LLM and fine-tuning it to output robot actions already, and then they're doing that currently with imitation learning from expert demonstrations. But if you subsequently use like RL, you don't even need the expert demonstrations, or you can like generalize to more different kinds of tasks that were not in your expert demonstrations. So I see this as something like very interesting to try. And yeah, if
I think the
somebody
idea of
here,
fine-tuning LLMs based on environment feedback is a different idea from RLHF. Because RLHF is more like you align to humans. But this fine-tuning with environment feedback is like when your environment changes, you will slowly learn how to deal with it as well. So
right?
this is like the fast model in my fast and slow architecture, where you have a neural network to slowly learn the transitions or slowly learn the change of an environment, right? So in my case, it's given a state and a goal, you output action. So I think this is feasible. It's just very slow to learn because it takes a while before your changes in the environment will lend themselves to the weights of the large language model or neural network.
Okay, I
So
see.
in order for an agent to learn faster, there needs to be a memory module, which is the slow module of my fast and slow.
Okay.
So I do agree with what you're writing here. So I am not completely against this feedback from the environment, but I disagree with learning from reward. That's why I
Okay,
disagree.
interesting. Yeah, actually, what I'm arguing here is essentially RLHF. Yeah, as you said, RLHF is used for alignment. It's the general picture is pre-training gives you the capabilities, and then RLHF aligns the capabilities to like instructions, right? And all I'm saying is maybe something similar works for robotics, where pre-training of LLMs on like internet and robot data gives you the general robot capabilities that we want, and then like RL is used to align the capabilities to tasks that we want to complete, for example. So it's interesting to like think about and explore this space, I think. Yeah. Yeah, next slide, please. And so on the whole, this is like my concluding slide. Thank you to the one person who is still here. So LLMs are a powerful source of semanticity, and they improve many parts of the robot learning pipeline, or they have been like proposed to improve many parts of the robot learning pipeline. And this was just like a brief survey of many things that I think are promising. And we don't know like what's the best yet. But I think the paradigm of just training end to end is like a remarkably simple recipe that has been proven to work. And, as John says, it's like throwing data at the problem. But, sometimes that works and that's what you need. So it could be, very highly practical to just do this for like things that we care about. And the question then is like how to scale the data, which is, the central topic of like this talk. And we kind of, I think like it's also important to think about like better evals for LLMs in this space, because currently we don't really have a systematic way to evaluate, the proficiency or the capabilities of LLMs for like various kinds of robotics tasks. And it would be useful to have more evals for specifically geared for things like that. Like the LLM, the AI safety folk have already developed tons of evals and like infrastructure to test for many things like manipulativeness or honesty or etc. fairness. And I think the robotics people could take a leaf from that and just try to recreate that. Yeah. Okay. So that's the end of my talk, I think. Yeah. And thank you for coming. Thank you for listening. I appreciate any feedback that you can give on my talk. If you go to this link, it brings you to a Google form where you can tell me how I did. And I'm happy to take any remaining questions.
Yeah, so maybe we can just have like 5 to 10 minutes of questions. Anyone want to ask anything? Or I can start with one. Actually, I got one question I wanted to ask all along. I've been
Yes.
asking a lot. Yeah, before I ask the question, yeah, thanks so much for preparing this deck of slides. This
Yeah.
80 slides didn't come easy. I think
Yeah.
you just digested years of robotics and LLM papers into one, like I'll call this like a mini lecture. So yeah, really appreciative of that. Yeah.
You're
So
welcome. Yeah.
and I
Thank you.
also
Yeah.
wish you all the best for your remainder of the PhD, because this topic is really quite hot, and it's we all don't know the limits of LLMs and like how much you can interface it with robots. So it's very exciting to do that. Although
Yeah.
our initial approach of what works might be different. I mean, you like end-to-end learning. I prefer modular
Yeah.
hierarchy. I mean, you say reward is good, but I
Oh
come
no,
from
I also like, and I also like modular things actually. It's just like it's very hard to argue against the surprisingly simple formula, right? Just train end to end on everything. It's like if you try to convince someone that they shouldn't be doing that, and then they'll just show you the data and say like, oh well this works, it scales, but it's like it's almost frustrating that like, it's so hard to tell them to come up with counter arguments for that. But yeah, I agree. Like
don't worry. I mean, in the pursuit of my ideas in 4 years I submitted in the RL field, I have never gotten a single paper accepted because ideas
oh,
are too different from the mainstream. So
right.
I can totally understand why like people are still doing this, because this has been the paradigm. It's hard to shift this paradigm when all along in the past 20, 30 years, everyone has been talking about rewards, optimization, and so on. Yeah. But that's not the kind of system I seek to develop, because it is very slow to adapt. You
Yeah.
take an Alpha Zero system, train it on a new game, you take days to learn it. Yeah, depends on how good your compute is. Stuff like RT2, you can work well because you have high compute, high amounts of data. That
Yep.
works well, great, good for your use case, but it doesn't really, I mean, you really need a lot of data for this. So I'm more interested in systems that can scale well with very little data, very little like experimentation, because that's like more or less how humans learn in the world. So I'm trying to create stuff like that. And I mean, different focus, I guess. Yeah, both work.
Yeah.
Yeah,
It's fair
both
enough.
have different use cases. So I wouldn't dismiss the other field as well. It's just not my
Yep.
interest.
Yep. Totally fair.
But what do you think are some of the challenges of getting robots to like learn fast? Like for example, you saw your experiments just now, and like some of the papers. So
To
far, it's
learn
like
fast.
demonstrations
Right.
and a lot of similar tasks. But how do you
Yeah.
think we can get the robot to like generalize outside of the distribution?
Yes. Okay. Yeah, that's a good question. If we make an analogy to humans, right? Like one reason you can think of humans as being, say, able to adapt so quickly is that we already have a bunch of prior experience on which to base the adaptation, right? Like we are not we are kind of genetically programmed at birth with certain instincts or reflexes already, and then like through our years of experience, we collect, like we learn about the world, and then we learn about the world in ways that we can generalize to like new situations. So I think like the prior knowledge is what enables fast adaptation. And currently in robotics, the way to imbue your models with prior knowledge has been like large scale pre-training on large data sets. So that is the existing paradigm, and I'm sure there could be others. I just don't have I just don't know what they are at the moment. But I would say that adaptation is something that essentially has to be based on like knowing how to adapt in like similar situations.
So you're saying that the basis functions or the primitives need to already be there.
Yeah.
Adaptation is just simply choosing a different set of functions to meet your new environment.
Yeah, you could say that. It's like you know what generally works, and then you just choose like among those primitives, as you say.
Yeah, it's interesting because I've been thinking about parallels to humans. Like we definitely only can do certain things: walk, run, jump. There's a lot of other things that we cannot possibly do. So our worldview is also grounded by what we can do. Like we don't think of flying, because we can't fly. I
Yeah.
mean, maybe next time when you have devices, you can expand your worldview. So I
Mhm.
do think that there's a limit to how much we can adapt, and it's all based on like what we can do. I think it's more based on the action space that we can do.
Yeah, okay, right. Yeah, I think, yeah, definitely for, any particular individual, right? Like the space of what they can do defines, how they are going to adapt to different situations. And like but as humans, we have the ability to expand our action space, right? We invent technologies and stuff. So it's useful to think about stuff that we can't do at the moment, but, if like if you could do that, then what could you do by doing that? It's one path I would say to adaptation. Like you can change your environment, or you can change yourself in such a way that you can like expand your action space.
Mm. Actually, on this point, I think memory plays a huge role in adaptation as well, because when you go to a new environment, you tend to do the same stuff that you did in your previous environment most of the time. Like shift house, you try to organize your house in a similar way, try to make things feel similar to what you've been seeing through before, like some habits and stuff. Which also means one thing: humans don't make good robots. Okay, because like for example, robots. What do we want robots to do? We want robots to perform the task exactly. We get bored of that.
Yep.
Second, we want robots to optimize for a given environment, like play chess and beat us, find the most fastest way to drive, that kind of stuff. Humans don't optimize. So we operate on a different system here. We don't exactly do the stuff that traditional robotics is striving to do. So
Yeah,
there
yeah,
are differences, but because of these differences, maybe that's why we adapt better, because we don't necessarily seek to optimize. We can just use a base set of rules to just guide our behavior in something new.
yeah. That's interesting. I guess what you're kind of saying is that like um maybe robots have overfit to a particular environment or something, and that's why
Yes. And the overfitting is thanks to
they don't generalize.
optimization due to
Right.
reward function and the
Yeah.
Bellman optimization methods used in all
Yes. Yeah.
robots.
Right. Yeah. So yep, I agree. And we were coming back to like you know in robotics, the prevailing paradigm for how you get like how you resolve this is just train the robot in more environments. Now how scalable that is an open question. Like will the whole internet of like text and image and video data be enough to get like a robot that is truly generalizable to the whole world? Maybe and maybe not, and we'll have to like see, because no one's done it yet.
Yeah, cool. And anyway, yeah, that's all I have. Last 1 minute. Anyone else want to ask anything? Okay. If not, if anything, just feel free to use this QR code to give Daniel feedback. And yeah, thanks so much for sharing, Daniel. And yeah, we will talk offline more because I
Yep.
think it's good to have some of the robotics community, some ideas to discuss with. Because for me, what I'm lacking is I don't have a robotics community here. All the stuff I'm doing so far is I watch videos, read papers and stuff. So it's good to talk to people like you.
Oh, yeah. Well, we would be happy to chat more in the future. Yeah.
All right.
Oh, yeah. Thanks again for having me, John. Thanks to
All right.
everyone for
Thanks.
listening.
Thanks, everyone.